Hey everybody, today we're talking about how derivatives affect the shape of a graph. In this video, we're going to talk about the question qualitatively and visually. In our next one, we'll get into it a little bit more algebraically and quantitatively. So here I've drawn the graph of a function, y equals f of x, and immediately looking at it, I can say a few things. I see a local maximum at x equals 3. To the left of that, the function's increasing. Immediately to the right, it's decreasing. Then at x equals 4, I've got a local min, and the function goes from decreasing to increasing. To the right of 4, then the function is increasing. What about the derivative? Well, we remember that the derivative is talking about the slope of the line tangent to the graph at any given point. So let's get a tangent line in here. I'm going to start near the left endpoint of the interval, where we said that the graph was increasing. And as we look at the tangent line here, we see it has a positive slope. Therefore, the function has a positive derivative. And in fact, that's going to be the case everywhere here to the left between 2.5 and 3, wherever the function's increasing. The function goes from increasing to decreasing at 3. And once the function's decreasing, we see that the tangent line is now pointing downwards. The slope is negative. The derivative is negative everywhere from 3 to 4. To the right of 4, we again have a tangent line with a positive slope. Therefore, the derivative is positive. Great. Let's go back to x equals 3 for a second. This is a critical value, in fact, a local maximum. So at the value x equals 3, the function goes from increasing to decreasing. The derivative goes from positive to negative. Derivative changes from positive to negative, local max. At x equals 4, similarly, the derivative has gone from negative to positive, and we have a local minimum. Now, as it turns out, that's always the case, and we can enshrine this as a theorem. Let's see this on the following slide. Okay, so if a function f is differentiable, then the sign of the derivative tells us whether the function is increasing or decreasing. Positive first derivative, increasing function. Negative first derivative, decreasing function. Now, all of this assumes that the function is differentiable. It's not differentiable, doesn't make sense to talk about the derivative. Also notice that we're talking about this on intervals. Doesn't make sense really to talk about whether a function is increasing or decreasing at a point, right? The second part of this slide is describing the first derivative test, which is a way of classifying whether critical values are local maxes or local mins. In particular, if x equals c is a critical value and the derivative changes from negative to positive at that value, so the function goes from decreasing to increasing, then you've got a local minimum. Similarly, if the derivative changes from positive to negative at that critical value, so the function changes from increasing to decreasing, you have a local maximum. Finally, if the derivative does not change sign at a critical value, you know you don't have a local maximum or a local minimum. So no sort of extremum at all. Again, this is called the first derivative test. Let's see a qualitative example. So suppose we know just a few things about a function. We know that the derivative is 0 at x equals 3 and x equals 5. So those are critical values. And we know the derivative is negative to the left of 3 and to the right of 5, and positive elsewhere, so from 3 to 5. We know a few things right away. We know that the function is going to be decreasing wherever the derivative is negative. So that means to the left of 3 and to the right of 5. Similarly, we know that the function is going to be increasing wherever the derivative is positive. So between 3 and 5. Finally, since the derivative changes from negative to positive at 3, the function changes from decreasing to increasing at 3, we have to have a local min there. And since the function changes from increasing to decreasing at x equals 5, the derivative goes from positive to negative, we have a local maximum at x equals 5.